Welcome to part 2 of your chapter 15 notes on waves. In this video, we're going to talk about some of our wave properties and the calculations that we will end up doing in this chapter. So wave properties, there are a bunch of different properties that all types of waves have. And the properties that we have are going to depend on the type of energy that's making the waves. So most waves will have these similar properties, but if we have a sound wave or a light wave or a wave from an earthquake, a seismic wave, we might have slightly different or varying properties because of that. However, all waves have these same properties, and the first is a wavelength. Wavelength is, like its name suggests, the length of one wave. More specifically, it's the distance between one point on a wave and the exact same place on the next wave. So for example, here we have, let's get my laser pointer here. Here we have, we can measure the wavelength from measuring the top crest of one wave to the top crest of another. We could measure the bottom trough of a transverse wave to the bottom trough of another transverse wave. Or we can measure the starting point. So here we've hit the kind of axis here, our starting mean position of the particles. And when we hit that again, not here, but right there, the distance from this point to this point would also be our wavelength. And actually, it doesn't matter where you measure the wavelength from, as long as you measure the same place on the starting wave and the next wave, you're going to have the same wavelength regardless of whether you use crest to crest, trough to trough, or mean particle position for each. So that's our first property. And again, it doesn't matter whether it's a transverse wave or longitudinal. Our wavelength for longitudinal waves, we're going to measure from compression to compression or rarefaction to rarefaction. Again, same spot on one wave to the exact same place on the next. Second property is called frequency. Frequency is how many waves go past a point in a second. So kind of like the name suggests, how frequent, how many waves do you have? We measure our units in hertz, which is capital H, lowercase z. And a hertz is just a fancy way of saying 1/second or a per second. The higher the frequency, that means the more energy we have in the wave, because we have to have more energy to make more waves go past in the same amount of time. So for example, if 10 waves go past in 1 second, that means my frequency is 10 hertz, 10 waves per second. If I have 1,000 waves go past in a second, that means my frequency is 1,000 hertz or 1,000 waves per second. And if I have 1 million waves go past in a second, then that means my frequency is 1 million hertz or 1 million waves per second. In order to get 1 million waves to go by in a second versus 10 waves to go by in a second, the wave just needs more energy. It needs to be moving quicker and needs more energy in order to do that. So that's our second wave property that all waves have. Our third wave property is the amplitude. Now, the name amplitude doesn't necessarily give away what this one means. The amplitude means how far the medium moves from rest position. Rest position is when it's not moving, when that medium that it's traveling through, whatever it may be, solid, liquid, or gas, when it's not moving to the farthest position it moves when the wave comes by, that's the amplitude. Now, a couple things to remember. For a transverse waves were all of our light waves and electromagnetic waves. The highest point is our crest and the lowest point is our trough. Here we've got our crest up here, trough down there. We want to know the furthest distance those particles or the medium moves. So normally they're on this rest position, this solid black line. And when the wave comes by, they can either move this far up or this far down. These two arrows, up or down, are equal to each other. They're just in different directions. So if we want to measure our amplitude, we measure from the resting position to the top of the crest or from the resting position to the bottom of the trough. And it doesn't matter whether it's just traveling through air or whether it's traveling through, in this example, it kind of looks like it might be traveling through water or a solid, where we can actually see the motion changing. And again, the highest point is going to be our amplitude. The lowest point will also be our amplitude. Notice that it's not measuring from the top of the crest to the bottom of the trough. It's measuring from the middle of the wave to the top or the middle of the wave to the bottom. Now, in compressional waves or longitudinal waves, so these are our sound waves, remember that the points where the mediums close together are your compressions, and the area where the mediums spread apart are called your rarefactions. Now, it's a little harder to measure the amplitude on one of these waves. Here we've got our compression, and here we have our rarefaction, because what we want to measure is one individual little, in this case, slinky ring, and we want to watch where it moves and how far it moves, and that's going to help us find the displacement, which would be our amplitude. The closer together our compressions are, and the more stretched out our rarefactions are, then the larger our amplitude will be. Now, we're not actually going to measure amplitudes for longitudinal or compressional waves. We will only measure amplitudes for, let me backtrack here, for our transverse waves. So again, we're taking from the starting position of the particle or the middle of the wave to the top or the middle of the wave to the bottom. And we can actually get measurements, distance measurements, whether it's in meters or nanometers or something like that. Okay, our last property is wave speed, and this is when calculation will come into play. The speed of the wave, how fast it moves, depends on what it is traveling through. So whether it's traveling through a solid, a liquid, or a gas. Now, waves in general are going to travel faster when they're traveling through gases than they do through a liquid or solid, because there's less particles for them to have to work through, and there's more motion that those particles can have. We will calculate wave speeds, and we will do it using this formula. Wave speed is equal to the wavelength, so the length of the wave, times the frequency, how many go by in a second. Our wave speed is going to get the units of meters per second. That's what every speed has. Our wavelength is a length measured in meters, and remember, frequency is hertz, which is the same as 1/seconds. So if we're taking a meter times a hertz, which is 1/second, that's going to give us a meter per second for our wave speed. In variable speak, this looks like V for the speed. So V, it measures our speed. We get this kind of upside down Y. This is called a lambda. That's the symbol for wavelength. And F is for frequency. And so we're going to do a practice calculation here, calculating the speed. But one other thing I want to note is this is a 3-variable equation. At some point, we're going to have to solve for maybe the wavelength, or we're going to have to solve for the frequency when given the other 2 variables. All right, so our example. We have a wave that has a wavelength of 2 meters and a frequency of 500 hertz. We want to know its speed. So the question's asking, what is its speed? We're going to start by writing our speed formula, where V, the speed, is equal to lambda, the wavelength, times the frequency. Then we're going to fill in. 2 meters was our wavelength. We can see that right here. And we had a frequency of 500 hertz. So we plug in 500 hertz for the frequency, and then we solve. 2 meters times 500 hertz gives you a total speed of 1,000 meters per second. Remember, our speeds are always measured in meters per second. And in this case, our sig figs work out, but always, again, remember, double check. Whatever your least amount of sig figs is from your starting values, that's how many sig figs your answer has to have. In this case, it's just 1. Now, I mentioned on the last slide, we're not always just solving for speed, although you'll see on your test hints for this chapter that one of your calculation short answer problems is solving for speed, but we also need to be able to rearrange. So just like when we were dealing with density earlier this year, we can take V equals lambda times F and put it into our triangle. So notice if I were to solve for frequency here, I'd cover it up. I'm sorry, I don't know why they made that purple. But if I solve for speed here, I cover it up and I have frequency times wavelength. If I want to solve for wavelength, I cover it up and I get speed over frequency. If I want to solve for frequency, I cover it up and I'm left with speed over top of wavelength. These 2 purple blocks are reversed. This top one should be purple there. This bottom one should be purple there. But regardless, you can see that we can put it into our triangle to help us rearrange and solve for the other variable. And as I mentioned, if you look at your test hints, question number 26 on your test tells you to calculate the wavelength, when given the speed and frequency. So you're going to be given speed, you're going to be given frequency, and you're going to need to solve for wavelength like we are in this formula. And question number 27 says calculate the frequency when given the speed and wavelength. So you're going to need to be able to, again, rearrange your speed equation to solve for wavelength and to solve for frequency. And once you rearrange it, you just plug in your numbers and solve. Okay, this is it for this video. We'll move into our part 3 video, which is going to deal with when our waves change direction, and then a little bit more about specific light and sound waves.